Okay, so welcome to the second lecture on Foundations of Cryptography. Let me briefly remind you what we did last time. So we had our first definition of security for encryption schemes. We defined encryption schemes as these tuples of algorithm, key generation, encryption algorithm, decryption algorithm, and we have also the key space, the message space, and the ciphertext space. And then the goal we want to achieve with encryption schemes is confidentiality, which means that we want to encrypt data so that the encryption doesn't reveal information about the underlying plain text. Okay, and our first definition of, or more formalization of this goal of confidentiality was perfect secrecy, introduced by Claude Shannon. And it says that such an encryption scheme consisting of these three algorithms is perfectly secret if for every distribution over the message space, every message and every ciphertext that appears with non-zero probability, we have that the probability of the message M conditioned on the ciphertext being C is the same as the unconditional probability for the message space. The idea is that an eavesdropper, an attacker, adversary, sees the ciphertext, so he knows what this is, that's why we condition on it, and then he wants to guess what the message space is, and this is sort of the probability that he has for each message space. But this says if this is the same, then observing this doesn't change his probability over the messages, which simply means that he doesn't get any information about the message given the ciphertext. Remember the example, you don't get any information from this course, from this lecture, if the probabilities of giving you correct answers after the course is the same as before the course. Right? Then you gain no information from the lecture. Here we always have, as I said, we always assume that we have a probability distribution on the key space. That is defined by this key generation algorithm that defines the probability distribution on the key space. Here we always also assume that this is true for every probability distribution. Then we saw, given a probability distribution on the key space and the message space, which we assume to be independent, we get an induced probability distribution on the ciphertext. We have this simple formula that splits this up into all pairs of keys, messages that end such that the message encrypts to this ciphertext given that key. So all this makes sense, and then we can define in the usual way conditional probabilities as simply the ratio of the conjunction of these two events divided by the probability of this event alone. Okay, so this is kind of, once you get used to it, it's a very intuitive definition. Right? You just have to understand what these probabilities and the equality of the probabilities means. Okay? It often says that this is the a posteriori probability of the message, and this is the a priori probability for the message space, and so observing doesn't help you. The disadvantage of this definition on this level of perfect secrecy is that here, to check whether a scheme is perfectly secret given this definition, it looks like we have to look at every probability distribution over the message space, which is kind of annoying because there are infinitely many of those. Even if the message space is finite, there are infinitely many, uncountably many even, probability distributions, so it seems to be hard to check. So that's why we wanted to have other definitions of perfect secrecy that are equivalent and that do not talk about the distributions on the message spaces, but only over the scheme itself. And this was the equivalent definition that we had. We said that, or we proved that the private key encryption scheme is perfectly secret if and only if for every pair of messages M0, M1 and every ciphertext, the probability of M0 being encrypted to C over the random choice of the key, that's why there is this set K here, is the same as getting the ciphertext C as an encryption of M1 over the choice of the key defined by the key generation algorithm. Right? And this is a much nicer definition because it doesn't talk about the probability distributions over P at all. Okay? And using that definition, for example, we could show that the one-time pad is perfectly secure. The one-time pad on L bits is defined as follows. I will use it today, so that's why I'll recap it here. Here, the key space, the message space, and the ciphertext space are all the same. They consist of 0, 1 to the L, where L is some parameter. The key generation algorithm chooses keys uniformly at random, and then the encryption is simply done by component-wise XORing the key and the message, bitwise, which is possible because they both are keys and messages both have L bits. And the decryption is done similarly. And then if it's correct, well, if you decrypt, you XOR K twice to M, and that gives you M back. And one can easily see that this definition here is satisfied by the one-time pad. That's because for every M and every C, there's exactly one key that encrypts this the message M to the ciphertext C. Namely, the key is M XOR C. Just manipulate the equations here, right? If you want this to be C, some fixed C, then you just have to set K to be M XOR C. So, and then we have that the probabilities for the one-time pad here, it's always 1 over the keys, the size of the key space. And that's independent of the particular message that we pick. Okay, so the one-time pad is perfectly secret. This is a little different formulation of Shannon's theorem that I presented to you the last time, because this makes clearer what the consequences are. This follows from the other version that I had, and the other version follows from this version. They are all mostly equivalent. So Shannon's theorem says that if we have a private key encryption scheme and we want it to be perfectly secure, then we need that the key space must be at least as large as the message space. So we cannot get away, and that means we cannot get away with short keys. Okay? If we want to encrypt messages, we have to have long keys. The keys must be as long as a message. And we cannot use a message, the key twice, because then you just concatenate basically the message, and then all at once the key is no longer as long as the message, and that doesn't give you perfect secrecy. Which means that to achieve perfect secrecy, we have to invest a lot. And it's really not it's not practical in most scenarios. As I said, there are a few scenarios where the one-time pad is still used, probably still used. But in other applications, in particular, everything related to e-commerce or anything that you probably want to do over the internet, this is not practical. Okay, good. So perfect secrecy is prohibitively expensive. And that is the reason why we have to look at other definitions of confidentiality that are almost as good as perfect secrecy. They're just a little bit weaker in some sense, but they avoid this expensive property of perfect secrecy. And also what we want to achieve, and that is the major sort of the major part of a large part of this course is this here only guarantees confidentiality against eavesdropping attacks. The adversary, if you go back to our definition of perfect secrecy, the original one, here the adversary simply observes, sees one ciphertext, and given that one ciphertext, he wants to deduce what the message was. In practice, adversaries can do much more. And I will go back to this when we come to these more refined versions of security definitions. So, and we want our security definitions to also cover these more advanced adversaries, okay, that go beyond just eavesdropping. So it's too expensive, and it's also not good enough, right? So we need something else. And the first step towards that direction, or in that direction, is using first another equivalent definition of perfect secrecy, but this definition leads to the refinements of defining confidentiality for encryption schemes. And this is actually the way we, in modern cryptography, define security in many scenarios. And it actually catches some of the intuition behind perfect secrecy also very well, this definition. And as I said, in modern cryptography, we often define security via games or experiments. Games or experiments between challengers and adversaries. And the way we do this here is defining perfect secrecy is you imagine you are an adversary and I'm the challenger, and I say, look, if you claim to be able to break perfect secrecy of my encryption scheme, you should be able to do the following. You give me two messages, I encrypt one of them, and then I just give you the ciphertext. And then you should be able, which of the two messages that you gave me I picked. If you can do that, I believe that you can break my scheme. If you cannot do that, and if no adversary can do that, then it should be perfectly secure or perfectly secret. And this is the formalization of this game. So it's between, we have this private key encryption scheme for which we want to define, perfect secrecy. And then we have this eavesdropping game between the challenger and the adversary A. And it's denoted in this funny way. Priv stands here for private key, priv K, private key. Eavesdropping, because we only look at eavesdropping adversary. This will change. And pi here is the scheme, and A refers to the adversary. The challenger is always doing the same thing. But this is defined for every adversary. And the game is defined as follows. The challenger chooses first a key K with a key generation algorithm from the encryption scheme. Then A outputs two messages, M0 and M1, of his choice. He can pick any two messages that he wants. And then B chooses a bit B uniformly at random. This is the notation for picking a bit uniformly at random. So B is 0 with probability 1/2 and B is 1 with probability 1/2. And he computes C as the encryption of MB. So if the bit B is 0, he encrypts M0. If the bit B is 1, then he encrypts M1. So this is the way we pick the random message from the two that the adversary computed. And then he sends C to A, and A outputs eventually a bit B prime. How he does it? It's the definition of A. No, I don't care at this point. And the result of the game is 1 if A guesses correctly which of the two messages was encrypted. And otherwise the result is 0. Okay. And then we can visualize this as follows. Here it seems a little bit just another way of visualizing this, but it turns out that this visualization will help us a lot to understand these things and also do kind of our security proofs later. So here we have, on this side, we have the C. here we have our A, and we can visualize the game as first we pick the key according to the key generation algorithm that's done by C. Then A picks these two messages, M0, M1. Unlike here, where I really say this is done according to the key generation algorithm. That's the way the challenger does it. Here, I do not specify how A does it. It's up to A. Right? It's the definition of A, and I don't make any assumptions on A. So I just say, you just have to give me two messages. How you do that internally, I don't know. And then we pick the bit, we encrypt, we send C over. So here you see the communication between the two boxes. You see the communication between the two parties. And then you get this bit B prime. Again, I do not specify how he does it because I'm talking about later on about all A's. So this is just the input-output behavior and what C does. Okay, so later on, we will put in here something. That's why it's a large box. When I talk about security proofs, I will put in here something. Okay, and then we denote by this thing here the output of the game. It's a bit. And we say that the private key encryption scheme is perfectly secret, or that this is theorem, if and only if for every adversary A, the probability that the output of the game is 1, that the adversary wins, is 1/2. And that's for every adversary. For every adversary, this game is defined. For every adversary, this particular value is defined. And then also the probability that it's 1, that he wins, a particular adversary wins the game, is also defined. And I want it for all adversaries to be 1/2. What does that mean, that it's 1/2? If you go back to this, I require basically that the C doesn't give him any information about what I picked here. Right? Because if it does give you any information, you can exploit that information to compute this B prime or get a better guess on B prime, on B. 1/2 you can always achieve, right? Just output 1, for example. It's correct because here it's picked uniformly at random. Right? And then with probability 1/2, you're right. And so 1/2 you can always achieve by very simple strategies, and this definition says, or this theorem says that it's perfectly secure if and only if you cannot do better. And so also what I want to say, this is an if and only if. So if it's perfectly secret, then for every adversary, this is 1/2. And if this is for all adversary 1/2, then it's also perfectly secret. So it goes in both directions. The one direction we briefly discussed, namely that if it's perfectly secret, then this is 1/2. And this follows basically directly from this characterization. Because this characterization says that the C here that you get by encrypting either one of two messages is independent of the message itself. Because what you see, the C has the same probability of appearing no matter what M0 or M1 is. And that's true for all pairs of messages. And hence, if you go back to this part here, this game here, this C here is independent of this bit B, stochastically independent. And since it's stochastically independent, that's the only information that A gets about B. And if it's stochastic independent, then his choice is independent of B. And then it's the same with probability 1/2. That's just how things are. Okay. So, and this is kind of this definition of security via this game or these games. And in here, that will be our starting point for relaxing, but in a controlled way, our security definitions. Okay. First relaxing and then strengthening, okay. But keeping the relaxation. Okay. So far, so good. Good. So now we want to move on to, okay, so for further use, I often, or basically all the time in the subsequent lectures and definitions, I will use the following definition. So if you can see here, what I'm really interested is in the difference between the two values here. This here, the probability of the output of the game being 1 and this and 1/2. Okay. So and that's why we define the advantage of an adversary in the eavesdropping indistinguishable game by the absolute value of the probability of the adversary A winning the game minus 1/2 in absolute values. Okay. So that's called the advantage. How much better is he doing than simply guessing by picking the bit uniformly at random? And this here said for every adversary the advantage is 0. There is no adversary that can do better. Okay. I put in here absolute values because it's necessary. It's sometimes technically it's a pain sometimes. But later on I will a little bit argue that you can ignore it. In the lecture notes I'll do it slightly more formally. The reason I will usually ignore it, because if you are you only have two choices. If you are more likely to be wrong than right, as I said last time, that's almost as good as being more often right than wrong if you just have two choices, because you just can flip your choices. Right? If you're more often wrong than right, flip it, and then you're more often right than wrong. That applies only for binary choices, no? Because otherwise you cannot flip. Okay. So that's why in subsequent lectures I will ignore it, although technically it's necessary, as we'll see. Okay, good. Any questions so far? If that's not the case, then we go to our next definition, or our next part, where we relax our definition. In this part, I still will only consider eavesdropping adversaries. They just listen, don't do anything fancy, but we'll relax our definition so that it makes much more sense. And in the way that we can actually define schemes that achieve this security definition bit without being prohibitively expensive, under certain assumptions. And if you remember last time, I told you cryptography, we usually need to make assumptions to prove security. But we want to make, in this course, I want to make very general assumptions. General assumptions that give us a lot of flexibility, not specific, usually number theoretic assumptions, but general assumptions. Objects of a very general type exist, and not assumption this particular object has that property. Because by that I have this flexibility, and if some object turns out not to have that property, well, I moved on to something else. So that gives me more flexibility and more confidence, actually, that the assumption is true. Right? Obviously, it's easier to assume, or more likely, there exists an object with this property than say, this object has that property. Okay. So why can we relax perfect secrecy? If we can relax it, it must do something that's too much, right? Or consider things that are too powerful. And the one thing where it's too powerful, it offers too much security in two senses. First, the adversary learns absolutely nothing given the ciphertext about the message. If you just learn a tiny little bit, but I can't really sort of quantify how much you can learn at most, but it's a tiny little bit. That's not that bad. Right? Instead of saying nothing, I say really, really, really tiny, but positive. Yeah? Which will relate to the advantage is not going to be zero. It's really, really, really small, but it can be positive. Yeah? And the second thing where it offers too much security is we looked at all adversaries. And we don't care about adversaries whose running time exceeds the lifetime of the universe before they have an output. That's irrelevant, right? If the running time is so large that the adversary will only finish when the universe has collapsed or whatever the physicists tell us it's going to happen, we don't care. Okay. The security of your credit card number, if that becomes public in 15 years, probably you moved on to a different credit card anyway. The credit card number is no longer valid. You don't care. Okay. There are really short-term things that you want to protect. There are also things that you want to protect for long times. For example, genome databases. Typically, you want them to be protected for a long, long time, even beyond your lifetime, because you may not want that your offspring, they share a lot, they share the genome with you. If that becomes public, yours becomes public, then the genome of your offspring becomes public, basically. So that needs to be protected much better than some information, some sort of information that's like credit card numbers or even other things. So we need not look at adversaries that have prohibitively large running times. We only need to look at adversaries that have reasonable running time. And in fact, the way that we usually define in computer science and theoretical computer science, reasonable running time is polynomial time. Right? But then we don't, in this course at least, I'm not going to say, like, I'm only considering polynomials up to this degree, say n to the 100 or so, any polynomial time. So that's, again, very powerful, but it's just polynomial time. So I'm restricting the set of adversaries that we consider. Okay, so that is how we can relax these two things, and we'll see today how we exploit this to relax our security definition. And then perfect secrecy, and that's the way how we enhance it later, also offers too little security because it only considers eavesdropping attacks. And adversaries are usually much more clever. They do not just eavesdrop, they try to manipulate things. They become active. Okay? Eavesdropping is often called passive attacks. They just listen, but they become active. They try to induce you to do things that are stupid or that they can exploit. Right? They try to make you do something that they can exploit. Then it's active attacks. Okay, and I said it's too expensive, so we can use this here to get rid of this the expense that is induced by perfectly secret encryption schemes. Let me remind you one thing, or recall that keys can only be used once. That's what we said. But what you also need is that keys usually, to achieve perfect secrecies, are picked uniformly at random from the large keys space. Right? And if you want to pick something, so you have the key space K, if you want to pick something uniformly at random from this key space, you need to generate so-called random bits. And you need to generate randomness. Right? And this here is 2 to the log of size K, right? And to pick an element uniformly at random from this set, you need to pick that many random bits, truly random bits. Yeah? Because if you have, assume that this is a power of 2, right? This is a natural number for the time being. So you need to have true randomness, lots of true randomness, because the key space is large in perfect secrecy. True randomness is hard to get. In fact, we don't really know how to get it, basically. Physicists tell you that certain decaying processes, they are sources of true randomness. Actually, that's a little bit debatable, but anyway, we assume that we can get those things, and we are confident that some of the methods that we have are good enough, but it's expensive to generate these bits. So we would like to get away with as little randomness as possible. So this is also going to be a concern. And if I say here true randomness for me always means uniform randomness. And there is other randomness than uniform randomness. There are other distributions than just the uniform distribution. Okay, and that's going to be very important in this course, because in general we look at other distributions. Okay. So the consequences are we consider restricted adversary, polynomial time adversaries. We consider more powerful attacks, not just eavesdropping. That will be chosen plain text attacks and later on chosen ciphertext attacks. These are considered to be the ultimate goal that we want to achieve. We relax our security requirements in controlled fashions. And relating to the last point that I mentioned, this one here, we will often use pseudo-randomness as much as possible instead of true randomness. Pseudo-randomness is, I will define it formally, is things that look like they are random to certain adversaries but are not. That's why they're called pseudo. Okay, so let's go to this part here. And I will be very brief because, as I said, I assume that you are familiar with this polynomial time formalism, as you have heard about it in algorithm courses or courses on complexity theory. So we restrict adversaries to polynomial time algorithms, but we also allow the adversaries to use randomness themselves. They are probabilistic polynomial time algorithms. Okay. And I abbreviate that by PPT, probabilistic polynomial time. Yeah. So polynomial time algorithms, what is that? That simply means that the output, the algorithm outputs a result after polynomial many steps in the size of the input. So if you talk about the polynomial time algorithm, you always say the number of steps is polynomial in the size of the input. So you have to know what the input size is. Otherwise, and that makes some of our definitions a little bit more complicated than what we saw in the previous lectures, because we have to specify an input. And let me go back to that. If you remember, when we talked about our encryption scheme so far, we had these 3 algorithms, right? Keygen, the encryption, and the decryption algorithm. For the encryption, we had basically two inputs, right? The key and the message. Okay, so which I denoted by this. So these two things are the inputs. Okay, so there is a well-defined input. The same is for the decryption algorithm, which gets a key and a ciphertext. But we didn't have any input here. But if I want to talk about a probabilistic polynomial time algorithm, also for the schemes itself, not just for the adversaries, also the schemes must be efficient. You don't want to use an encryption scheme that takes time 2 to the 1000, because that will not finish in your lifetime. Yeah? But what is what's then is an input to the key generation algorithm? And what we do in cryptography, modern cryptography, we specify a security parameter. That gives us sort of the level of security that we want to achieve. Okay? And we specify that in a very particular form because we specify that in unary. So in subsequent definitions, this will be 1 to the n. And 1 to the n is not 1 times 1 times 1 times 1, but it's n ones. Okay? So 1 to the n, not this, but it's a string of n ones. Okay? And then polynomial time in the input then means polynomial in n. Okay? So if I say that this algorithm is polynomial time, its running time must be polynomial in n. Okay? If I would write down here instead of this, I would write down n. Its input length of n in binary is only log n. And being polynomial in log n is completely different from being polynomial in n. Okay? What this means in particular is if this algorithm is allowed to run in time polynomial in n, it can specify output keys of length n. And that's basically what we mean by our security parameter. The security parameter often specifies, look, this is the length of the keys that you should output. Okay? And the length is variable, and this specifies how long the key should be. And the schemes that we define, the idea behind all schemes that we define is if we increase the key length, security increases as well. Okay, so by giving this security parameter, we specify the key length, and the key length hopefully says something about how secure the things are. Okay. Since we talk about polynomial time, this will be always related to polynomial time. There's also a way where they do that more concretely, and then this would be really much more precise. Then something, if I say there security is, say, 80, then this should mean that no, in the concrete setting, which I'm not going to use, but this could mean that no adversary that has at most 2 to the 80 steps should be able to do anything useful. Here we will say anything that polynomial in n can do something useful, and here for key generation the algorithm runs in polynomial time. Okay, so this is how we what we'll see in my definitions later on. This is the idea. So as I said, also these algorithms must be probabilistic polynomial time algorithms. You want the key generation to be efficient, you want the encryption to be efficient, you want the decryption to be efficient. That's just because these things should be useful. This refers to the usefulness, not the security, in sense of finishing in reasonable time. And then we consider only polynomial time adversaries. And if I say I will consider only polynomial time adversaries, the polynomial time, again, polynomial time in which input? And the input is always the input parameter, the security parameter, sorry. This security parameter, if that n, then no polynomial time adversary in that security parameter. Okay? So it also specifies then what kind of adversaries we look at. Okay? And that's important. So this is all these things are measured polynomial time basically in the security parameter. Here it's a little bit different because we have k, which is defined basically by the security parameter, but m could be much longer than the security parameter. You want to encrypt messages that are arbitrarily long, basically. Okay, then you say, okay, it's polynomial in the key length and the message length. Right? Of course, if you want to encrypt gigabytes, you should have more time than if you want to encrypt kilobytes. And the same is here, true is here. Okay, but I said we look, so far I talked about polynomial time adversaries. Now, but I didn't talk about so far about probabilistic polynomial time adversaries. What is a probabilistic algorithm? And so let's fix a little bit of notation and then talk about probabilistic algorithms as well. So if I have a finite set S, then by this notation, U left arrow S, I say that this denotes the process of choosing an element from S uniformly at random, which means that every element U in S is chosen with probability 1 over the size of S. If I have a set using the absolute value notation, I denote the size of S, the number of elements, which makes sense since it's finite. Yeah? So this is always the process of choosing something uniformly at random. I always assume that we can pick elements chosen uniformly at random from finite sets. Yeah? And in fact, what we can see is actually one of my favorite exercises, is to choose an element uniformly at random from any finite set. It suffices if you can choose from a 2-element set uniformly at random. That's good enough. Once you can do that, you can pick from any finite set an element uniformly at random. So you need to be able to pick random bits, uniform random bits, or you need to be able to toss a fair coin, one that comes up heads or tail with probability 1/2 each. And a probabilistic algorithm is an algorithm that can do exactly that, on top of all the other things that it may do. It can pick or toss a fair coin as often as it likes, right? And gets a sequence of random bits. So it has the capability of tossing coins. Formally, I often denote that a little bit differently. What we often say that, or the way we often view this, or should view this, is that a probabilistic algorithm that has input x also has a second sort of hidden input, r, from 0, 1 to the L length of x, where L is some function. If x is a bit, let's say x is a bit string, right? Then the absolute value of x is a number of bits in x. Right? So then it has this hidden input that is chosen uniformly at random, i.e. every bit string of this length appears with the same probability, namely 2 to the minus length of x. And then it can just read off these bits one by one. Right? And the costing of a fair coin is then just reading the next input bit from this R, reading the next bit from R. We go through this. And once we have an algorithm that can toss coins, you usually think of an algorithm as on input X, it produces a fixed output. If it can toss coins, it need not produce a fixed output. The output may as well depend on the coin tosses, on the random bits that it has. So formally, the output of A on input X is no longer a fixed value. Instead, it's a so-called random variable. Right? A random variable that takes on certain values with certain probability. Huh? Yeah. And we denote that by this notation here. Probability of A of X is U denotes the probability that A on input X outputs U. Let me make that more precise or more concrete using this notation here. Okay, and to do that, what's sometimes useful is I write this here as the output of A on input X if the random bits that it has are R. Yeah? So this is the output of A on input X with random bits or random bit string R in 0, 1 length of X. Okay? I make a semicolon here because it's like the hidden input. Right? Huh? And then this probability is the following. It's the size of a certain set, namely the size of all R in 0, 1 length of X, such that A of X with this particular R gives us the output U. Divided by this here, right? It's the number of R's that lead to this output U given X divided by all possible R's. This is because I assume that this is truly is uniform. If you have a uniform distribution, it's always the number of things that lead to the event that you want divided by all possible random, the size of the random space itself. Okay. No? So this is how we define this, how this probability is defined. No? And often by this notation here, A of X, left arrow U, we denote the process of running A to obtain an output of A on input X. Whenever I use these arrows, I usually have a random process. If on the right-hand side, I have a finite set, this is always uniform. If I have here an algorithm, I mean, this here R is picked uniformly at random, and then I run A on X, comma R, and the probability then for every particular U is as defined on the board. Oh, Yeah. And the probabilistic polynomial time algorithm is a probabilistic algorithm such that there exists a polynomial P with the following property. For every input x and all r in the set of the randomness, algorithm A on input x and r halts after P of length of x many steps. No, that's so independent of the randomness that we use. The upper bound on the running time is always is fixed. Huh? And this P must be a polynomial. If you look at this and think about it for a second, maybe 2 seconds, you see that if the algorithm can only run for that many steps, then this function here must be upper bounded by this here, because he cannot read more bits than he has time. Right? Reading a bit from this thing is one time step. You think about Turing machines, whatever. Don't think about too much about Turing machines, but reading a bit or tossing a coin is at least one time step. So, and if you have only that much time, you may as well assume that this here is not longer, because the rest is useless to you anyway. Even going there, you have to jump over all the intermediate bits, right? That really refers to Turing machines, not random access, but never mind. Okay, why are we interested in probabilistic polynomial time algorithms? First of all, key generation must be probabilistic. We pick keys according to some random process. Keys are secrets. If there is no randomness involved, there are no secrets. That's one thing. And the other thing is, obviously, also for adversaries, we should consider probabilistic polynomial time adversaries. We are not just looking at adversaries in practice that always succeed. Right? Adversaries may use randomness to succeed most of the time, significantly often, things like that. As I said, if your banking information is revealed every 1,000 times, or 100 times you use it over the internet, that's bad, because eventually it will be revealed. So also for the for adversaries, we should look at probabilistic things. That did not play a role for perfect secrecy, because in perfect secrecy we looked at unlimited adversaries, not restricted to polynomial time. If you have unlimited computational power, you don't need randomness. That's one thing that you can think about that makes sense. So this is the one thing that we are going to use, probabilistic polynomial time algorithms. And probabilistic polynomial time in this sense. Okay. These algorithms are sometimes called Monte Carlo algorithms, as opposed to Las Vegas algorithms that have a slightly different semantic. Then there are also Atlantic City algorithms, but these are, anyway. Okay, good. The next thing, unless you have questions, the next thing I want to talk about is when I said that in perfect secrecy, we required that the advantage of an adversary, of every adversary, is 0. And I said we want to relax that as well. The advantage is allowed to be tiny, small. We need to specify what we mean by tiny, small. And the way we use that in modern cryptography is using the notion of a negligible function or negligible functions. As I said, negligible, the term negligible means basically you can ignore it. Right? The negligible for us means for all practical purposes it's 0. It's not, but for all practical purposes it is 0. The way mathematically we specify that is as follows. A function mu from the natural numbers to the non-negative integers is called negligible if for all positive c's there exists an n0 in n such that for all n larger than n0, mu of n is upper bounded by 1 over n to the c. If you remember your definition of a continuous function, this looks like these things, like the quantifiers that you have here. What does that mean? N to the c, c is fixed. For fixed c, n to the c is a polynomial of degree c. This is 1 over inverse n to the c. What this says here, for every polynomial, eventually, namely if n is large enough, this mu becomes smaller than 1 over this polynomial, for every polynomial. So eventually it's smaller than every 1 over polynomial. This eventually being this here. Okay. Let's look at a few examples to get used to this notation and this this term. And we'll go through a few examples. I claim that 2 to the minus n is negligible. The function 2 to the minus n is negligible. Huh? Let's see, 2 to the minus n. So mu n to r. I write this, once I write this really formally, n is mapped to 2 to the minus n is negligible. Okay, so how do I prove that? For every c, okay, let's fix some, let c be arbitrary, but fixed. Huh? So. Okay. Then I want, what is my n0 now, after which I can say that 2 to the minus n is smaller than 1 over n to the c. Well, let's just write it down. What does it mean? 2 to the minus n is less than or equal to, let's say, n to the minus c, right? This is just 1 over n to the c. Okay, let's take a logarithm on both sides. Logarithm to base 2. When I take a logarithm unless otherwise specified, I always mean logarithm to base 2. Well, this means that minus n is bounded by minus c times log n. Okay? Which means that n must be larger than c times log n. Just multiplying by minus 1, flipping the inequality. Which is the same as saying that n divided by log n is larger than c. Yeah? So what I can say is set n0 to be, well, now I can fix an n0. Well, now I can say, well, do it. Say it's n 0, sorry, now I have to pick this C. Let's say n0 is, now what do I want? Such that this is the smallest, minimum n such that n divided by log n is larger than C. Yeah? Okay. And this is a finite number. Yeah. It's a little bit annoying to write this down, actually. But if you take n0 to be you can do this roughly C times log C. That works, roughly. And if you do this here is certainly less than C squared. If you do it C squared, then this is certainly true. Something like that. Okay? So in that case, I have such a thing. Okay. Well, doing this here all the time is kind of annoying. Right? Always doing these things. And what we usually do is, if we want to fix that, if we look at this mu of n, right? It's usually sufficient to prove that if we have mu of n, or n to the c divided by mu of n is 0. Yeah? You look at n to the c for all c. You look at n to the c divided by mu of n, and that should be, the limit of that should be 0. Yes. So let me check. 1 over let me yes, this should be mu of n divided by n to the c should be 0. Yes, this should be 0. Yeah, sorry. Yeah. Okay. Actually, that's even not, no, that's not true. Yeah, let's see. I want that 1 over mu, let me just do it. 1 over mu should be so this here, if you do it the other way around, let's just do this here. So what we want is 1 over mu of n is larger than n to the c. Yeah? So, and then we want this here, and in fact we want that this becomes arbitrarily small. So this should go to 0. So the real thing is n to the c times mu of n should go to 0. This is the way we want it. Okay. Should be 0, so equality. This is 0. And if you check this here in the example, you see that we have n to the c times 2 to the minus n, which is n to the c divided by 2 to the n. And you know that this is the exponential, and then exponential, this is polynomial. Polynomial divided by exponential goes to 0. It's a little bit annoying because I use here 1 over and here not, so that's why this becomes a multiplication. But anyway, okay, this is usually the way you actually prove this. You look at this product, look at the limit, use all the knowledge that you have from calculus, and then it's easy to see. And that's why you can see that this here obviously is not negligible. Because although this guy here is a huge number, it's still a polynomial, right? So it does not become smaller than this. If I add here a 1, right, do this here, this is 1, 2, 3, 4, 5, 6, 7, 8. So this is 100 million. Yeah, 100 million. If I look at C to be 100 million plus 1, then this is no longer true. Unfortunately. This here is a more interesting case. Because most people, sometimes people tend to think that, well, to be negligible, we have to have something like 2 to the minus n or something. That's not true. This here is good enough to be negligible. And I'll prove that briefly using this limit stuff. Let's look at this thing here. So what I need to do is I need to look at n, the limit. N goes to infinity. N to the c is fixed, times this mu of n, which is n to the minus log n. And I want this to be 0. Okay? So I look at the limit n goes to infinity of n to the c divided to n log n, which is the limit n goes to infinity of n c, or 1 over n to the log n minus c. Yeah? But this here, the exponent, goes to infinity as n goes to infinity, because c is a constant. And then I have 1 over n to something that goes to infinity, and this is 0. Yeah? This log n simply, eventually it becomes larger than any constant. Yeah? And that's good enough for this function to be negligible. I could even put in here n to the minus log n. I could put in here n to the minus log n, still negligible. Could put in an n to the minus log star n. Log star, funny looking function. Still negligible. Huh? So negligibility is something, it requires eventually smaller than any polynomial, but something like this is good enough. This here is not negligible, although this here is a huge number, but this guy here is only log n. And again, you can check that this is not going to work. Because basically, if you look at n to the c, this is 2 to the log c times log n. This is c times log n. Yeah? And if you look at this, then if I do the same thing here, this becomes log n in the exponent, 2 to the minus log n. That's not good enough. This n0 here becomes really, really large. But eventually, so for every c, you cannot find such an n0, because if n becomes large enough, it becomes too small. It becomes too large. So, yeah. Basically, what we need here, and then before we take the break, I guess, is a few rules that we have. And those are usually good enough for us to work with. And the rules are something that you look at in the exercises, I guess, as well. Is if you have mu1, mu2 negligible, then also the sum of the two things is negligible. Okay? The sum of two negligible functions is negligible. Okay? More interesting, even, although this is often good enough for us, but if we have mu negligible, p polynomial, basically something bounded by n to the c for some c, then p times mu, this function, is still negligible. Okay. This is because this here is true for all c, for all possible. If I multiply something with a polynomial, I just have to increase this n0, but eventually it still becomes smaller. Okay. So these are a few rules, and basically that's good enough for all that we want. Negligibility is the thing that we look at. If something's negligible, we can ignore it. It's as good as zero. In practice, that's not necessarily true, but anyway, for our theory, that's good enough, and that's actually the way we do it. Okay. So these are the two key ingredients that you need to understand for the following definitions. Probabilistic polynomial time algorithms, negligible functions. And then we can already define our relaxation of perfect secrecy, which I will do after the break. And we take a break for 15 minutes. Okay, we meet again at 9:45. Okay, good. Then see you in 15 minutes. So let's continue with the lecture. So we now have all the ingredients we need to go to our next security definition for private key encryption schemes. But first, I will give a refined definition of a private key encryption scheme that takes into account all these polynomial time things and security parameters and stuff like that. It just fills in some of the details that were not necessary for the perfect secrecy, and actually historically those things only showed up much later. So here's now our formal definition of a private key encryption scheme. It consists, as before, of the three algorithms: key gen, the generation algorithm, encryption algorithm, decryption algorithm, but now we require all three of them to be PPT algorithms, probabilistic polynomial time. The key generation algorithm, on input 1 to the n, outputs a key k chosen uniformly at random im01 to the n. This is not necessary, and we denote this by this thing here, okay? This is really what, I could do this more generally, but this is what we do actually in practice also. The key generation algorithm gets a security parameter, and then it picks a key really of this length as a bit string. Yeah? So it makes life a little bit easier. The input algorithm, the encryption algorithm, on input, it also gets the security parameter as input. So it knows this. Sometimes I will drop this. because it's always key. It gets a key, and it gets a message, which I assume for the time being to be from 0, 1 star. So we want the encryption schemes should be able to encrypt all possible bit strings. Right? And it outputs a ciphertext C, which is in general also from 0, 1 star. And we denote this by C left arrow enc K of M. Okay? As I said, sometimes I drop this here. This here is not included here in the inputs because it's always understood that it has to be there. The decryption algorithm on input 1 to the n, a key and 0, 1 to the n, so the two n's are the same, and the ciphertext in 0, 1 star. As I said, we want ciphertext to be bit strings. It outputs a message M in 0, 1 star, and the notation is the same. And our correctness requirement, that has nothing to do with security, is that for all security parameters, n, for all possible keys, for all possible messages, if we first encrypt the message with the key using our encryption algorithm and then decrypt the resulting ciphertext using the same key, then we get M back with probability 1. Okay. So the probability now is over the random choices here, but also because the encryption and decryption algorithm may use random bits, random coins, is also over the random inputs of the encryption and decryption algorithm. So no matter what the internal randomness, the coin tosses are, of the encryption, what the internal coin tosses of the decryption are, first encrypting with key K, then decrypting with key K gives us back the message. Always. Probability is 1. We always talk about finite probability spaces, so probability 1 really means always. Okay. So, and as I said before, when we talked about the private key encryption schemes in connection with perfect secrecy, this is just the syntactic requirement together with the correctness. It doesn't say anything about security. Correctness, or semantically, it's just consisting of these 3 algorithms, and we have this correctness requirement. Yeah. Good. So in practice and in many constructions, we will not be able immediately to encrypt all messages. And often we will be able only to encrypt messages of a certain size if we have a key of a certain size. Okay? And then there are general techniques that I'll discuss to lift that to 0, 1 star. Okay? But we will have a specific notation for that, namely we call the fixed length encryption schemes, where we say that we have a private key encryption scheme and we have some polynomial function, and then we only require that the encryption algorithm, if we have a key chosen with security parameter 1 to the n, works only for messages in this space here. So of a certain length, the length is determined by this L, this function L. Then we say we have a fixed length encryption scheme with message length L of n. Okay. Okay. And then, as we will see, there are general techniques to lift it from fixed length to what I had before. Sometimes it's convenient also to say this is up to length L of n. Here I say it's exactly length L of n. Sometimes it's convenient to just have up to length L of n, which I would denote by including here a, here I could include a less than or equal, okay? But it doesn't really matter all that much. Okay, but okay. So in general, when we construct things, will be in general first fixed length and then lifted. Okay, because our ultimate goal clearly is to have it for 0, 1 star. Okay, clear? Good. An example, the one-time pad is a fixed length encryption scheme with message length n. The message length is the same as the key length. So the function L of n is the identity. Now we need to define security. And we do that with a refined version of our eavesdropping game for private key encryption scheme. It's refined because we have this polynomial time requirements, and we'll also see that we'll define the advantage, or the requirement for the advantage is a little bit different. So the eavesdropping indistinguishability game, usually I would input here an n. Sorry, I forgot that here should be an n actually. On comment, it's again as before between the challenger and the adversary. They have the common input 1 to the n once. Okay, and the challenger chooses the key using this algorithm with input parameter 1 to the n that is known to both the challenger and the adversary. Then A outputs 2 messages, M0, M1, with the same length. Here I assume this is a private key encryption scheme for arbitrary length. And I will require that the adversary outputs 2 messages of the same length. That's a little bit different from what we had before. I'll explain the reason for this later. Then, and it sends those 2 messages to C. Now, C, as before, chooses this bit B, uniformly at random, and it computes the encryption of MB using the key K, which is unknown to A. Right? A outputs, it outputs the 2 messages, means it sends them to C. Here, it just chooses. It does not output them. It keeps them private. It's only for the challenger. And it sends the C to A. Now A outputs a bit B prime, and the result of the game is 1 if B is equal to B prime. And otherwise the output is 0. That's as before. So there are 2 differences. We have here the key generate, the common input. We have here the key generation, and we have here that the message length has to be the same. And we can visualize this as before. In addition, here this is a common input and comes from outside. Then C chooses this key. M has picks the 2 messages. I do not specify how it did that. It's just an A. Then we get this B, we get the C, and we get the B prime back. Okay. Come later on again why we have the same length. Now we write this private key eavesdropping A comma pi for the output of the game on input 1 to the n between, so using the scheme A and the challenger A and the adversary A. So for every adversary A, we have this value, which is a bit 0 or 1. It's a binary random variable. Binary can only take on 2 values, 0 and 1. And by this probability, denotes the probability that adversary A on input 1 to the n wins the eavesdropping game against pi. Yeah? And we call it also sometimes the success probability. And we call this here, as that I already had before, eavesdropping advantage of A against pi on input n, this probability here minus 1/2. As before, 1/2 you can always win with probability 1/2 just guessing. Okay, we want to know how much better. And this is called the advantage of A against pi in the eavesdropping game. Yeah? So now we are ready to, okay, let me skip this. I will come back to this later. And now we say that private key encryption scheme pi has indistinguishable encryptions against eavesdropping attacks, or simply is eavesdropping secure, if for every probabilistic polynomial time algorithm there is a negligible function such that the eavesdropping advantage is this eavesdropping function or bounded by this eavesdropping function. Sometimes I'll just, sometimes I also use this here, right, instead of equality. It doesn't really matter. It's sometimes easier. Okay? So the game is a little bit different than before, but this is mostly notational. But if you look at our definition of perfect secrecy, we have two major differences that relate to what I said earlier this morning. First of all, here we no longer have 0. Perfect secrecy required here 0. Here we say upper bounded by negligible function. So you can have an advantage be above 1/2, but it must be tiny, little, negligible. Okay. The second difference is we no longer look at all adversaries, we only look at probabilistic polynomial time adversaries. Probabilistic polynomial time adversary, polynomial time in what? What's the input to A? Which input, which parameter do we measure the running time? Yeah? Yeah, n. That's the only input that it gets at the start of the game, right? If you look here, that's the only input that it gets at the start of the game, 1 to the n. Which in particular means that it can only produce messages of length polynomial in n as well. Because if you want to output something, for each output bit, 1 time step, basically. Yeah. So we only consider adversaries whose running time is polynomial in n. And we view this always as functions. So for all n, and then we look at these functions. Otherwise, we did. Okay. Okay. Yeah. So this is the two differences where we deviate from perfect secrecy. We make it easier to achieve this definition. Only probabilistic polynomial time adversaries. We allow a negligible advantage. Okay. Why do we have this requirement here? And then I'll talk about the meaning of this. Well, if you encrypt two messages that have very different length, you would expect that the ciphertexts also have very different length, right? I mean, 0, 1 star, ciphertext length has to differ, right? And typically, short messages are encrypted to short ciphertext, long messages are encrypted to long ciphertext. So if I did not require this here, then a clever A would just, to win this game, would just pick a message, say, of 1 bit and one consisting of 1 billion bits. He gets the encryption of one of them, while he just decides depending on the length. Yeah. And there's no way you can avoid, I mean, you can avoid that, right? So this is just to make this non-trivial. What this intuitively says is, with our security definition will say the encryption doesn't reveal anything about the message except its length. Okay? Because this is something that we have here in there as a requirement. You cannot hide the length of a message base. Well, not the exact length, but sort of in which kind of roughly how long it's going to be. This is not something we cannot. If we want to do 0, 1 star as our plain text space, it's not possible. If we look at fixed length encryption schemes, this becomes vacuous, right? Because they have to be of the same length, because otherwise you cannot even use the scheme. Okay. Now, so this relaxation in this definition, what does this mean? This says that, and again, except for the length, the ciphertext almost gives you no information about the message. Almost no, because we have this negligible term in here. Can give you a little bit of information, but it should be really, really, really small. And we only look at PPT algorithms. We are not interested in algorithms that run forever, or almost forever. Those are not relevant for us. Okay. Yes. And the final part of today's lecture will be convincing you that this really is a good definition by giving you an example of what this implies. Just one example that implies a lot of other things about why we hide a message, or what it means. Okay. Okay. Let me give you, as I said, the eavesdropping advantage is this with the absolute values around this thing. This is, as I said, often annoying, and we would like to, and I argue that in the lecture notes in more detail, we can really assume without loss of generality that for all a's this is larger than 1/2. Or we only need to consider a's for which this is at least 1/2. If you have one with really much smaller than 1/2, just flip its output behavior, and you have one that's. It's a little bit more complicated because we have this n in there. Never mind. You can do that. We can really assume that we can really ignore these absolute values. And hence, the eavesdropping advantage indicates how much better it does than simply guessing the bit b. Because guessing then it's correct with probably 1/2. And throughout this course, I will make similar assumptions. And they are all without loss of generality. Sometimes I make these assumptions. Sometimes I don't make these assumptions, but it doesn't really matter. Sometimes making this assumption simplifies proofs a little bit. And then I make this. Okay, good. Okay, if there are no questions, then let's go to, this is already what we defined, what I already said. Let's go to an implication of this definition. I said that this definition should imply that given the ciphertext, you get no information about the plaintext except its length. Okay? So for example, it should imply that if I give you the ciphertext of a message, this ciphertext should not enable you to predict, say, the first bit of the message, except with roughly probability 1/2. Huh? That seems like a minimal requirement for this definition to make sense, right? And for our intuition to make sense. It should imply that you can, and of course, if it's true for the first bit, it should also be true for the second bit, the third bit, and so on. But I'll do it just for the first bit. Should also not reveal something like the parity of the bits in the message, not the majority of the bits, something like that. Right? If it doesn't reveal any information, all these things should not be revealed. In fact, there is a definition that seems it's technically more involved, but actually tells you there doesn't reveal any predicate about the message. So let's prove that this is true. If we have an encryption scheme that has this, is eavesdropping secure. Namely, let pi be a private key encryption scheme with message length L of n. This time I really require that it's of fixed length for technical reasons. That is eavesdropping secure. Then for all PPT algorithms A, there is a negligible function mu such that if I give you the encryption of a random message, the probability that you predict the first bit of the message correctly is not much more than 1/2. In fact, the probability that A, on input the security parameter, on input the encryption of M is M minus 1/2 is bounded by this negligible function where the key is generated uniformly at random. The message is chosen uniformly at random for the message space. And M1 through M up to Ln denote the bits in the message. Okay. Okay. So even for a random message, you cannot predict the first bit given the encryption. Yeah? Not just for particular messages, but even for a random one, you cannot do that. By the way, because we're talking about lots of probabilities, let me go back here, and this probability here, what is it about? What's the probability space that we are looking at here? If we talk about probabilities, there is a probability space, right? What is a probability space? It's over every choice that appears in this game, over every random choice. So it's over the probability of the choice of the key. It's over the internal randomness of A picking this M0, M1. It's over the random choice of B. It's over the random choices involved in encrypting. It's over the random choices of the computation that are involved in the computation of B prime from A. Over all these random choices is a probability. Okay? It's over the random stuff involved in this game. Okay? It's not over anything particular, so it's over for every A, over all the so it's over the randomness here, but it's also over the internal randomness of A that's used to compute these things and to compute this guy. It's over the internal randomness that may be used here. Okay? That's important to notice. Okay? Yeah? All the randomness that we have there. Because all this randomness is relevant for this. This here is a random variable. And this random variable is determined by all this randomness in this game. So that's why we have to do that, why we have to consider that. It's a binary random variable over all this randomness. And similarly, if I talk about this thing here, I talk about the random choice here, I talk about the random choice here, but I also talk about the random choice that A makes and the random choices that are possibly involved in encrypting. Okay. But also over these things here. The reason I have a fixed length here because I want to pick this method, the message uniformly at random. I cannot pick something uniformly at random from 0, 1 star. Infinitely large. That's why. Okay? So, this is what we want to prove. So, if it's eavesdropping secure, given the encryption, no probabilistic polynomial time adversary can predict the first bit of the underlying message except with roughly probability 1/2. Roughly, except this negligible factor in front of it. Okay. How can we prove something like this? Well, for every A, we have to do this, right? Using that it's eavesdropping secure. Okay. And here in the proof, I will use this assumption, as you see. So what we do now more precisely, we show this theorem by a reduction. When you understand the proof of this theorem, you will be able to mostly understand the proofs in this lecture. They are variations on this theme. There are sometimes, on few occasions, I have additional techniques. But the overall structure of the proof is always like this. This is kind of the easiest example of this kind of proof that we do. And what we do is, given an adversary A prime that predicts the first plaintext bit from a ciphertext, we use that algorithm to construct a new algorithm that distinguishes ciphertext in the eavesdropping game. Okay? So from one that predicts plaintext, we construct a new algorithm that we can use in our game here. Okay? But it's not immediate, right? Because in this game we have to generate messages. That's not something that the A prime will do, because in his setting he's not required to generate messages on its own. It gets something from outside. So there's something to be done. So this is the general theme that we have in all our proofs. We want to show that some security notion implies another security notion, and then we take an adversary against the other security notion, and from that construct an adversary against the original security notion. Here, predicting plaintext bits to distinguishing messages or ciphertext. Yeah? Good. This is like reductions you saw in complexity theory, right? Given an efficient algorithm that can solve, that can predict whether a graph has a Hamiltonian cycle, you construct an algorithm that can decide whether a Boolean formula is satisfiable or not. Something similar happens here. But what we also need to do is, like, if we have then to show several things. If A prime is a probabilistic polynomial time algorithm, then A is a probabilistic polynomial time algorithm. It's the first thing that we will need to do. Then we show that we can relate the advantages of the two algorithms in their respective settings, in their respective games. So we define functions. One is the eavesdropping advantage of A against pi in the eavesdropping game, and the other is this advantage of A in predicting the first plaintext bit. And recall that I don't use the absolute values. Okay? Yeah? So I define these functions that are the two advantages. And then we show that if this advantage of function is negligible, then this function is also negligible. Okay? But then we know that pi has indistinguishable encryptions. That's it. So for all PPT algorithms, the function delta as above must be negligible. Yeah? Okay. Therefore, for all A prime, the function epsilon is negligible. And here I use this step already, because I can argue that this is negligible only because for this A, because it's a PPT. And my definition for eavesdropping security only applies to PPT-As. So if I would construct from A prime, which is a PPT, something that's not a PPT, I cannot make this statement because the definition does not apply to non-PPT algorithms. And then I'm done. Okay, so from an adversary against plaintext prediction, construct an adversary again in the eavesdropping game, show that if one is PPT than the other, we relate the two advantages to each other in such a way that if the one is negligible, then the other is also negligible. And then we are done. And this is a blueprint for all our proofs. We want to show that something implies something else. We do this, use these adversaries from there to there, define these advantages, relate the advantages, show this, period. Okay? And keep always this picture in mind before you think about the details. But now we think about the details. So I will, oops, it's not good. Okay. I will do some of it on slides, some of it on the board. So let's go to the first step. So what I do is I start with a fixed but arbitrary A prime. I can do that for given any algorithm. And because I do that for any algorithm, I show for any algorithm this is negligible, so I'm done then at the end with my theorem. So let A prime be fixed but arbitrary. Against plaintext prediction. Okay. Now I have to, from this I have to describe the distinguisher A. Okay? Using this A prime. But since A prime is fixed but arbitrary, I cannot use anything specific about A prime. You cannot say, look, because A prime in the second step does this, or because it uses this if loop, I do this. No. I can only use sort of its input-output behavior. I can give it input, simulate it, run it, and see what it gives me back, and then work with the input. I cannot look inside of it. That's what we often call black box. It's a black box. We can put something in, something get out, but we cannot look inside the box. Okay? That is required by our thing. So now, if we want to get from the predictor to the distinguisher, we need to describe how on input 1 to the n A computes the two messages, right? Because we are in the eavesdropping game. And in the eavesdropping game, A computes two messages that it gives to the challenger. How does it do that? First thing. Second, when it gets a challenge ciphertext, A predicts a bit B prime. How does it do that in our case? Using our A prime. In both steps, we can use A prime as a subroutine. Turns out we will not do this here, but that's because this theorem is so simple. Okay, so that's how we do that. So to do this A prime from A, we set IBN to be the set of all elements in our message space that have the first bit as B. So this is the length and this is the bit. So IN0 is the set of messages that have the first bit 0. IN1 is a set of messages that have the first bit 1. Now think about it. You have an algorithm that predicts the first bit. Now you want that to construct a distinguisher. Well, wouldn't it be nice just to compute two messages where one has a bit 0, the other has a bit 1? And then if I get, and then now I have to distinguish which one was encrypted. I get my ciphertext back, and then I look what my predictor does, what the first bit is. And then depending on what he predicts, I just output whether it was M0 or M1. Right? That seems to be like the obvious way to use my predictor to get a distinguisher. Right? Use messages M0 and M1 that have different first bit. And I'm free to do that because we'll see that we can do that. So, okay, we do that. And then on input 1 to the n, our A chooses M0 uniformly at random from the set of all messages with first bit 0, and M1 as the set of uniformly at random from the set of all messages with input with first bit 1. Yeah? We'll see later why I pick these things uniformly at random from the respective sets. How can I do that? Well, I just pick the remaining Ln minus 1 bits uniformly at random and set the first bit 0 or 1. Right? Can easily do that in polynomial time. Yeah. Next step. Then the game goes on. C has already chosen its key. It gets the two messages M0 and M1, and it picks a bit B uniformly at random and encrypts MB. So eventually A gets the input C. And now I do what I just said. Now I use A prime as a subroutine, and I usually denote that by simulating A prime. I say I use it as a subroutine or simulate it. I simulate A prime on input C to obtain a bit B prime. See, what does it think the first bit of the message is? Huh? And then, quite obviously, I output this, and I output this bit that he outputs also as well. Yeah? This is my guess. Well, you see that M0 has bit 0, M1 has bit M1, so that's why this makes sense. And it's a nice way to visualize this, which we actually, that's why I have this large box in here. Okay? So this is we want to describe our A in the eavesdropping game. This is the eavesdropping game, the formalization of the eavesdropping game. And now using A prime that is fixed but arbitrary, I want to fill in what my new A does. Because I want from A prime to define an A. Okay? Now I fill in the details. And I can use A prime. That's why I put it inside here. Right? It's a subroutine that I can use. So we pick the two things as I described them. Send them over. This here, this here, this here. Now what I do is I forward this here 1 to the n, nc to A prime. Because this is what A prime expects. It expects a security parameter and it expects a C. Yeah? And then whatever it outputs, this B prime, I forward simply as my output. So it's a nice visualization of this thing. And I can do that for any A prime. For any A prime, this makes sense. Okay? Okay, yeah? Clear? So remember, I have to prove several things. We have first to show that if A prime is a PPT, then A is a PPT. Okay, let's go to this. This is the observation that I have here. This is this here. If A prime is a PPT, then what is a PPT? Why? It chooses these two messages. As I just said, you do that by just picking the remaining ln-1 bits uniformly at random. You can do that in polynomial time because we have a random. We can toss random coins, right? Huh? So this is polynomial time. This here is also polynomial time because the only thing that we do is we simulate A prime. We run it. By assumption, A prime is a PPT. So running is polynomial time. And then we just forward its output. It's a bit. So it's polynomial time. If A prime is polynomial time, and that's important because we run it. Right? We simulate, we run A prime as a subroutine. If that was not a PPT, then the whole thing is not a PPT. But because it is, the whole thing is a PPT. Yeah? And the second thing was we had to relate these two advantages to each other in such a way that if one is negligible, then the other is also negligible. In fact, what I will do here is I will show that both are the same. Right? And then obviously, by my blueprint, I'm done. Because then I know that, well, for any A prime, this constructed A is a PPT. Its advantage in the eavesdropping game is negligible. But that's also the advantage of A prime, namely epsilon n, in the prediction game. So that is the same, is also negligible. And I'm done. Yeah. Good. So we do that. This part here I'll do on the board. Okay. And there we'll see why this is important here. To do it this way. So let's look at the eavesdropping advantage of, this here was delta n, if I remember it correctly. Let me just make sure that I don't mess up my notation. Yes, this is delta n. And let me maybe go here. So delta n is the eavesdropping advantage of A against pi. Yes, pi on input n. Let me, okay, oops, sorry. Yeah, I will do it slightly differently because I will directly look at this random variable. Sorry. So I directly look at this random variable. Okay. And then on both sides I will subtract 1/2. We'll see that all things work out. And I look at the probability that this is 1. Okay. What's the probability that A pi wins this game? Yeah. Okay. Well, the way I defined A, this is exactly the probability that A prime on getting as input an encryption of MB outputs B. Because that's the bit I'm forwarding. So this is exactly by definition, this is the probability of A prime on input 1 to the n and an encryption of MB outputs MB. Right? Definition of my algorithm. Now I do the usual thing. I split things up. This here I can write as the probability that A prime on input 1 to the n and encryption of MB outputs B or outputs 0 and B is 0 plus the probability that A prime on input 1 to the n and the encryption of MB outputs 1 and B is 1. Huh? Just rephrasing the things, right? And splitting it up into 2 disjoint subevents. The next thing, again, don't think about it too much because I'm just using conditional probabilities. So I replace this conjunction by condition and multiplying by the probability of B0 being 1, being 0. So this is simply the probability A prime 1 to the n encryption of K of MB is 0 conditioned on B being 0 times the probability B being 0. Okay? Plus, and because I have only limited space on the board, we pick the bit B uniformly at random. So this probability here is 1/2. Right? Okay, this here is 1/2. And I do the same thing over here. That's the probability of A prime on input 1 to the n encryption of K MB outputs 1, condition B is 1, times the probability of B being 1, which is 1/2. Yeah. Okay. Did I write anything stupid? Oh, looks good. Okay. Here I condition on B being 0. Well, I just write that directly in here. So this is, and I put the 1/2 in front. This is the probability of A prime on input 1 to the n, comma, encryption. Well, here I condition on B being 0, so it gets M0. plus, and the same thing here, it's conditioned on 1, so this is 1/2 times the probability of A prime 1 to the n encryption K of M1 is 1. Yeah. Just pushing the condition inside what's there, right? Okay. But here, what am I doing here? This probability here, I claim, is exactly the probability that A prime on input 1 to the n, comma, encryption K of MB outputs B. Or actually that it outputs M1, M21. Sorry, I want this here. This is exactly the probability that A1 succeeds in his own prediction game. Why is that? Here, if I look at this here, what does A get here? All these choices also involve the choice of M0, M1 that I pick over there. Right? But if you go back here, in the definition that I used in my theorem, right? This probability of choosing M uniformly at random from 0, 1 to the L1, I can also describe this uniform choice as follows. First, pick the first bit uniformly at random. Or in other words, pick the set I and B uniformly at random. And then pick an element uniformly at random from that set. Okay? So this choice is really pick one of the two sets, with each with probability 1/2, and then pick an element uniformly at random from there. That's a uniform choice of a message. Okay? So what A prime gets in here as input, C, is really a truly random plaintext. The encryption of a random plaintext. Randomness here and randomness here. Together, this choice and this choice together is a random choice of an M. So what this guy here gets is really exactly what we have in our theorem. And therefore, it's the same here. Okay? And now if you look at the advantages on both sides, I would subtract 1/2. I can do that because I have no longer the absolute values. Here it really helps. Yeah? Yeah? That's why it's so important that I choose these things in this form here. Because I can only say something about the behavior of A prime if the input that I provide to A prime are exactly as in what I have in the prediction game. If I provide it with a different distribution, or its input has a different distribution than in its game, No, I don't know what it does. So I have really to make sure here in the construction, that's the art sort of in constructing this A from A prime. I have to provide A prime with an input that I can analyze in this black box fashion, just using my assumption. Okay? Or using what it's supposed to do. Yeah? So that's why it's important. I cannot just do here anything. I have to do it this way. But once I do this, I'm done here. And then, as I said, just subtract 1/2 on both sides, I get the respective advantages. And then I'm done. That's a proof. You should think about this proof for quite some time until you really understand it. And nothing in this proof was accidentally. Everything has to be done exactly the way I did it. You cannot modify this here. You cannot modify this here. If you do that, it probably will break down. No? And also get a clear picture. So get a clear picture of the reductions, what this means. Get a clear picture of then this instantiation and why I have to pick this in this form. And also make sure that you understand that when I talk about these probabilities, it's always like it's a probability. It's a probability about a lot of things, which I usually, sometimes I write them down explicitly because it's important for the game. This is the case here. Yeah? The game requires this here, defines it this way. Sometimes it's just from the algorithms itself. Okay. Once you understood this theorem, the proof, the rest will be mostly not too difficult. There are, as I said, there are 2 or 3 more tricks that we use, but this is mostly it. Okay. Questions? Also, don't take this as a random collection of symbols. Every single line in here has a meaning. I'm doing something meaningful. Splitting up an event into disjoint sub-events. Typically what we do. Conditioning. Typically what we do. Use a condition and then collect things again. We didn't come up by this by playing around with symbols and eventually hitting upon one of the Shakespeare plays or so. Right? That's not what I did, mostly. Okay, good. Then that's it for today. Next week, we'll go on to actually constructing things that have eavesdropping security and that can be built from general assumptions. And this requires pseudorandom generators. Okay, good. Thank you. See you next week.